We are entering a golden age in astronomy. Advances in technology are giving astronomers unprecedented capabilities, allowing us to explore the universe as never before.
We'll be able to understand our future and what our ultimate fate is going to be in the universe.
In the high desert of northern Chile, an international team of scientists and engineers is on a quest to unlock the secrets of the hidden universe. They are pushing the limits of technology to build the most advanced observatory on Earth in one of our planet's most inhospitable places. Known as ALMA, the Atacama Large Millimeter submillimeter array, this 30-year project promises to open a new window on the cosmos and redefine our place among the stars.
Whenever you build something that opens up new possibilities, and then opens up the new space of discovery. And that is a remarkable ability that ALMA will provide.
As humans, we're always asking questions. Perhaps the most fundamental is, where do we come from? To answer, we must venture into unknown regions of the universe, to its very edge, where the first galaxies are forming. Deep within immense clouds of gas and dust, where stars are igniting, and organic molecules are slowly building the ingredients of life. And inside dusty disks, where young planets take shape around their future suns. Such alien realms are separated from us by almost unimaginable distance and time, and are shrouded in veils of dust and gas. Are there other worlds where life has taken hold? How did they come to be? Today, we are on the verge of a giant leap in understanding. In one of our planet's most unforgiving environments, an ambitious new telescope is poised to revolutionize everything we know about our cosmic origins. It is called ALMA. Astronomers study what they can observe. For centuries, that meant stars, planets, and other visible objects. But the universe's deepest secrets may lie in the darkness between them.
Empty space is a little bit of a misnomer, especially nowadays in modern astronomy. Wherever we look with telescopes, we see something. There's gas, there's dust, there are stars. And whenever we look at a new unexplored region of the electromagnetic spectrum, we find something different.
Starlight arrives in every color we can see. But this visible light is only a tiny sliver of a vast electromagnetic spectrum that encompasses every kind of light we know of. We've been able to explore just about all of it, but one part has been especially tricky to observe: a range known as millimeter and submillimeter wavelength light, which represents half of the light that reaches us from distant space. Peering into this cold, dusty realm requires a telescope that goes beyond anything ever achieved in radio astronomy. Because the light they observe is so weak, radio telescopes must be built on a colossal scale. They have either a single massive collecting surface or an array of smaller dishes spread across a flat expanse. Combined, these individual antennas form a single giant dish as large as the entire array. ALMA is the most ambitious ground-based telescope ever attempted. The astronomer's design calls for 66 highly sensitive antennas, each costing over $5 million. Teams from North America, Europe, and East Asia are sharing the cost of the $1.3 billion project. Each region is responsible for its own antenna design and construction. The international collaboration and competition is drawing the world's top scientists and engineers, pushing the limits of innovation. ALMA's scientists need more than cutting-edge technology. They need a site unlike any other in ground-based astronomy.
There were three conditions. A place that would be high and therefore very dry, that would be flat so that we could put antennas, and accessible.
The number of high, big, flat sites in the world is very limited. And so the search for the ALMA site began in New Mexico, close to home.
There was a place called the Aquarius Plateau in Utah, which was pretty good. It's very high, but it turns out it has about 5 feet of snow on it all winter long. And you can't move the antennas around at all.
The site to end all sites, at least at the time for astronomy, was Hawaii. We studied the possibility of putting the array on Mauna Kea with the other big telescopes. And it just barely could fit. When we were asked, why aren't you looking at Chile? And so we made a trip to Chile.
The high desert of northern Chile is renowned for its clear skies. But the remote location presents huge challenges. Despite them, Chile remains the team's last best hope.
On the day that we went looking for a place, Geraldo Valladares and I drove along, going to higher elevation, heading up a very narrow old sulfur mining road.
Over ruts, around boulders, bouncing our way up.
We're having a good time, and we're headed towards something that's at least high enough to have flat ground.
We walk and look out, and it is just unbelievable.
Lo and behold, here is this enormous flat plain.
It's all really exciting. I mean, we felt like real adventurers.
The Atacama is the driest desert on Earth. Some parts have never recorded a drop of rain. What moisture there is typically condenses on the towering peaks of the Andes. Millions of years of volcanic activity have created perhaps the most unique feature in the region, the Chacnantur Plateau. This high-altitude plain stops the moisture-laden air rising from the Amazon basin. Its Mars-like surface provides the perfect terrain for cutting-edge radio astronomy. Finding an ideal site is one thing. Building the telescope in this extreme environment is another. The project faces significant hurdles. Not least of these challenges is the site itself. The 16,500-foot-high array operations site is the highest large-scale construction site on Earth. It is also one of the harshest. Temperatures fluctuate from -20 to 55 degrees Fahrenheit. UV radiation is almost double what it is at sea level. Winds are often clocked at 75 miles per hour. The conditions affect both man and machine.
The atmosphere is roughly half what it is at sea level, so you have half the oxygen. Manpower tends to suffer from oxygen deprivation. They tend to be lightheaded, they tend to be nauseous, and there's more subject to injury or accidents at that high site.
To deal with these risks, ALMA's design calls for a second, lower elevation site, the Operations Support Facility at 9,500 feet. Workers live here, just below the 10,000-foot level, at which high-altitude sickness increasingly strikes. But altitude and weather aren't the only dangers. The Atacama Desert sits above a fault line in the infamous Ring of Fire that encircles the Pacific. Earthquakes and landslides are common. Just to the southeast of the observatory, an active volcano called Lascar looms overhead. She sends an almost daily smoke signal of warning into the sky. The ash cloud from an eruption could paralyze the telescope for weeks. For the astronomers, these dangers are a calculated risk in their quest for new science. For the engineers, they present profound challenges. ALMA's builders must find materials and designs that deliver unprecedented performance in this unforgiving environment. If they succeed, this international team will change astronomy forever. In the quest to discover our cosmic origins, engineers are building the most complex observatory in history. Of utmost importance are the antenna dishes. Measuring 12 meters across, a main ALMA dish is the business end of a highly sensitive instrument. To maintain its precise shape, the dish needs to be rigid, yet very light, and must not warp in the heat, cold, and wind of the Chilean desert. With such stringent requirements, the engineers need highly specialized technology. Located on the Netherlands' southern coast, The Hague is home to a producer of composite materials uniquely suited for the challenges of the ALMA project. The telescope's design calls for 24 pie-like segments, joined together to form the backup structure for each dish. They are made from millions of tiny fibers.
The only material suitable for this structure is composite material. It's lightweight, strong. It is very stiff, and thermal expansion is almost zero.
4,000 individual sheets of fiber material make up each segment. Technicians must layer the precise shapes by hand, as the fibers can be easily damaged at this stage.
It's very strong in this direction of the fibers, but when I make a bend, I break it.
The finished segment is then baked or cured in a giant high-pressure oven. This hardens and strengthens the fibers. The engineers use a laser measurement system to verify its shape to within 20 microns, 1/5 the thickness of a sheet of paper. It takes weeks to craft a single segment. In all, the team will construct 600, each of them identical. 140 miles away in northern Germany, the segments are tested together for the first time. Like a circular jigsaw puzzle, technicians build the dish piece by piece over a period of 2 weeks. It's the only way to ensure the shapes are exactly to spec. The team's final step is to verify the position of the 1,300 grommets that will hold the dish's reflective surface. Every one is measured to a precision of a few thousandths of a millimeter. The dish is shipped in pieces to the ALMA site in Chile, where it will be rebuilt one final time. Far across the Atlantic, in the flatlands of East Texas, the antenna's other half, the finished base, is beginning its own journey. Outside of Houston, a team of 30 workers is moving the first North American antenna pedestal to the Gulf of Mexico. Because it takes up the entire road, they can only transport the huge structure at night. It's almost dawn when the caravan arrives at the harbor. The pedestal will spend the next 2 weeks in the hull of an ocean freighter bound for Chile, where engineers will attempt to join it with its dish for the first time. The next great leap in astronomy is underway. To encounter some of the great mysteries of modern astronomy, we don't have to look far into our own galaxy. Only 175 light-years away, in the constellation Hydra, is a young star that could be the key to understanding how our own solar system developed.
There's a wonderful protoplanetary disk around the star TW Hydra. This is a unique system because it's one of the closest known to the Earth, so we can see it in the most detail.
Only 10 million years old, 1/500th the age of our sun, TW Hydra is a planetary system that is just starting to take shape.
We know that there's an inner hole in the disk. We think that the hole's being cleared out by a planet in formation. And with ALMA, we should be able to see the gas and dust that's forming the planet, and even the gas and dust in the circumplanetary disk that may be forming moons around this planet.
ALMA's views of TW Hydra and other planetary disks will shed light on the earliest history of our solar system and could tell us where to look for other Earth-like planets suitable for life. On our own planet, life flourishes in even the most unlikely places, and the Atacama Desert is no exception. Here, a number of creatures thrive in the barren expanses. Flocks of Andean flamingos depend on the salt flats for survival. Desert foxes and wild donkeys comb the lush lowlands in search of food. And in the high desert, well-adapted climbers like llamas and vicuñas forage nimbly on the rocky slopes. The Atacama also has a unique human history.
The Atacama Desert is the center of this ethnic group called Atacameños. You see the remains of ancient civilizations. Before the arrival of the Spaniards, it was sort of a remote outpost of the Incas, very sparsely populated. Even today, you find original people.
The delicate nature of the area presents environmental challenges for the expansive ALMA project.
The desert is something you must take care of. You want to keep the natural beauty of the place. So we are being very environmental friendly.
One of the region's most imposing features is known as the Valle de la Luna, or Valley of the Moon. Carved over millennia by wind and water, the otherworldly landscape lives up to its name. Almost a month after leaving Texas, the antenna pedestal must make its way through the valley's narrow passages. After a 5,000-mile journey, it finally reaches its destination, the 30,000 square foot hangar constructed for final assembly of the North American antennas.
This is the site erection facility. This is the first place that the entire antenna assembly comes together.
The first major step in the assembly process is also the most risky: attaching the dish to its base. Using a 100-ton crane, engineers slowly lift the 14,000-pound dish structure 60 feet into the air. Foremen on hydraulic lifts relay commands to personnel on the ground, who steady the dish using a system of ropes. The final positioning can only be done by hand. Even a small bump can damage the dish. The 39-foot dish is aligned in the exact center of the pedestal.
We good? You good? Yeah, I'm good. Okay, give me that.
The antenna may look complete, but it's still missing a critical component: the reflective panels that gather the light from space. Deep in mainland Europe, on the edge of Germany's Black Forest, metalworking specialists create the telescope's precise dish surface. 264 aluminum panels, each about the size and thickness of a coffee table, sit on top of the dish structure. The different shapes fit together to form a perfect 3D parabola. Panels begin as high-grade aluminum slabs that have already passed stringent materials testing. To transform them into precise shapes, technicians use a specialized 5-axis machining instrument. Different titanium carbide drill bits hollow out the interior in a 2-hour process, making the panels lightweight but stiff. The team uses a coordinate measurement machine to verify that each panel's shape is perfect. They digitally map every surface to make sure it will fit with the others. The first time the reflective surface is assembled is upon arrival at the ALMA site. Technicians follow a strict sequence as they carefully transport them, one at a time, up to the antenna. To secure the panels correctly, they have to go inside the dish itself. Small holes in each segment create a tunnel with just enough clearance for one of the team's smallest workers. He will spend upwards of 4 hours at a time inside the dish's hot interior. The elaborate process takes nearly 3 weeks. After stringent testing, the engineers turn the antenna over to ALMA scientists to be readied for the move to the high site. They are responsible for checking every detail of the engineer's work, inside and out. Their long list of tests takes months to complete. The team and the antenna still face their biggest test to date. the move 7,000 feet up to the array site, where years of design and development will confront the raw power of nature. To discover our deepest roots, we must unlock the secrets of the early universe. Some 13 billion years ago, shortly after the Big Bang, we encounter a powerful beacon in the dark. This is a quasar, a newly forming galaxy anchored by a supermassive black hole. Quasars are among the most luminous objects in the universe. They're surrounded by vast oceans of invisible gas that will one day become stars. Seeing this process remains a challenge.
We know very little about what the gas is doing at these very, very distant early times in the universe. And ALMA's going to completely open that up for study for mankind. It's really the next major step in our understanding of galaxy evolution.
Light from the distant universe reaches ALMA's dishes as extremely faint waves. To capture them requires a complex suite of microscopic sensors and electronics known as the front end.
The signals that come in are extremely weak, and the front end has to be very, very sensitive in order to detect these signals and to amplify them to a high enough level that they can actually be processed.
The antenna works by collecting light, which is focused on a central mirror and reflected down into the center of the dish. Here, the light is directed into one of several tiny apertures, each leading to a receiver that is tuned to a certain frequency. The delicate receivers must be cooled to 4 degrees above absolute zero.
The amount of noise that's generated by any electronics is proportional to its physical temperature. So the colder you make something, the less noise that it adds to the signal.
Inside a temperature-controlled clean room, technicians carefully install the receivers into the front end using a precision guiding instrument. The front end is shipped fully assembled to the ALMA site. In the Chilean desert, ALMA's scientists and engineers prepare for the most critical event in the early life of the observatory. They are 24 hours away from moving the first North American antenna to its final destination on the Chatnantur Plateau. Decades of design and testing work are on the line.
I think we've been through so many tests to test the what-ifs that I honestly believe that barring anything that is just an absolute unknown out of left field, by late afternoon tomorrow we're going to set the antenna down on a certified foundation at the high site. We're going to plug it in. It's going to operate just like it was operating here at the test facility.
The engineering team performs critical tests to make sure no mistakes happen during the real thing. The success of the move hinges on the electrical connections between the $11 million antenna and the specialized transporter that will haul it into the high desert. The ALMA transporters are engineering marvels. Custom built by ALMA's European partner, these two 33-foot wide, 66-foot long behemoths are designed to carry loads in excess of 100 tons. Their 28 wheels have independent drive and steering control, allowing them to maneuver to within millimeters of a specific spot. The transporter drivers are equally specialized. There are fewer than a dozen people in the world licensed to operate these precision monster trucks. Drivers steer from the transporter's main cab. then use a specialized remote control from a distance when making fine movements. The transporters will be used throughout the observatory's lifespan to move the antennas for maintenance and to reposition them in the finished array. At ALMA's low site, preparations for the antenna move are going smoothly. But then the team encounters a problem. A vital electric current is not reaching the main receiver cabinet.
We did not find a 24-volt connection between the antenna and the transporter. That 24-volt source is very critical in communication between the antenna and the transporter.
Without this connection, the emergency stops that cut power to the transporter will not function. Five hours later, the engineers are almost a half day behind schedule, and additional tests still need to be completed. The lead scientists call an emergency meeting to discuss the situation.
So we don't have communication between the transporter and the antenna.
What really contributes to that?
In the case of a fire or something, we don't have any signal to the antenna, to the transporter.
As if there is a fire, are we going to get some alarm going off somewhere if there's some notice?
The team makes a difficult decision. They will proceed as planned, with all safety personnel on high alert. The 25-mile road that snakes its way through the mountains up to the Chaknantur Plateau is the observatory's most dangerous feature. The steep slopes require hairpin turns and high embankments. The road is especially hazardous for the heavy trucks whose drivers must breathe the thin air to take supplies up and down. ALMA's personnel take every precaution possible, but mishaps still occur. Since construction began, there have been 33 major accidents, 3 of them fatal. With the historic antenna move only hours away, the risks are very real. At ALMA's low site, nearly 30 years of work is about to culminate in a single day.
Okay, good morning everybody. Today is the day. About the weather condition, wind are increased around 11. We are worried to leave from here as early as possible for obtain the best condition for this movement.
Project engineers prepare to move the first North American antenna 7,000 feet up into the Chilean Andes. With so much at stake, there's tension in the cold desert air.
One challenge that we have no control over is going to be the weather, the wind, and the chance of a snow out, and we get halfway up the hill and we've got to either park or turn around and come back.
Already up against the clock, the team performs final safety checks. Driver Luis Roa positions the transporter with careful precision. 115 tons of antenna are lifted into the air. Including the transporter, the total weight is nearly 250 tons. Rescue teams in front and behind guide the transporter up the mountainside, at the ready in case of a mishap. To protect the antenna, maximum speed is restricted to 12 miles per hour. They will have 5 hours to reach the top. On the plateau above, desert winds are already reaching dangerous speeds. Part of the team arrives in advance to brave the sandstorm and keep the antenna pad drill holes free of sediment. Even a small buildup of dirt could prevent the antenna from locking correctly to the pad.
They look pretty good. Put a bolt in. Take the bolt.
On the steep slopes below, progress is slowed by repeated stops for safety checks. Finally, the antenna makes its way for the first time onto the moonscape of the Chaknantur Plateau. The dust storm is now in full force. After 25 miles of steady climbing, the most critical step remains: setting the antenna down. In 55-mile-per-hour winds, Luis directs the transporter with careful precision and locks the antenna into position on the first try. Yesterday, the critical power transfer failed. This time, it works.
Today is a very momentous day for us. Basically, it's the culmination of 8 months of activity on the antenna. This is the real stepping stone for us to completing the array.
After decades of preparation, ALMA is mere months from its first large-scale observations. October 2003. The aurora borealis, or northern lights, are seen as far south as Texas. But their beauty does not imply celestial calm. They signal a coronal mass ejection, a load of charged particles hurled by the sun at more than 1,100 miles per second. This one is so strong, it cuts power to more than 20,000 homes and knocks out communications throughout the Northern Hemisphere. It reminds us how little we know about our closest star.
The sun is a challenging object, astronomically speaking, for astronomers because it's so big and it's so bright.
ALMA will study the sun's chromosphere, a violent layer of gas just above the visible surface, helping us understand and predict solar storms.
You need something that can look at very bright objects, but also can give you a lot of resolution because these regions that you're interested in typically are quite small. ALMA can do that, and it can do it on short time scales. So that's the important thing. You'll get these movies, essentially, of how these active areas develop. It tells you about that space weather environment and how these things do actually propagate into the Earth and can affect our daily lives.
Light from the sun and other objects is received and amplified at the front end of each antenna. The telescope's back end is where it is combined and processed for astronomers to study. To produce high-resolution images, the antennas must be precisely synchronized using a device called an oscillator.
The ALMA local oscillator is the main tuner for the entire array.
Each antenna is equipped with an oscillator for each receiver. They are synced together via hundreds of miles of fiber optic cable to one central oscillator that controls the timing of the entire array. The required precision is on the order of a few femtoseconds.
Femtoseconds isn't a word that I don't think I was even familiar with before the project started. It's so short. 1,000,000 times 1,000,000 times 1,000 times smaller than a second.
In other words, it's the time it takes for light to travel the thickness of a sheet of paper. With more than 10 miles between antennas, an error of even a few thousandth of a millimeter could ruin observations. The enormous data stream from each antenna presents another unique challenge, one that requires a custom-built supercomputer. The ALMA correlator.
Every antenna is producing 96 gigabits per second of data, night and day. That's enough to fill up a DVD in less than a second. In a personal computer, you have 1 or 2 or sometimes 4 processors, and all the data that you're working on has to go through a processor, be worked on and manipulated, and come out the other end. In this machine, we have 128 million processors.
Built and tested in Charlottesville, Virginia, the correlator is the most powerful supercomputer in the civilian world.
It would have cost about $1 billion worth of PCs to do the arithmetic that this machine does. So it was clear that we had to build a special machine to do the calculations.
The correlator is housed at the technical building at the high site to minimize its distance from the antennas. It will handle some 17 quadrillion calculations every second and provide astronomers with 800 gigabytes of new data each day. With the correlator and 3 antennas now installed, ALMA is ready for its initial test as a working telescope. For the scientists, it's a critical milestone in paving the way for large-scale observations.
We should be able to actually begin the commissioning process of the telescope as an integrated unit, not just testing individual antennas, which is what we've been doing up until now. I mean, there are many telescopes around the world that are bigger or similar size to an individual ALMA antenna, but today we start working with the antennas all working together.
They will now move on to testing the telescope's abilities as a tool for cutting-edge astronomy. A tool that will search the cosmos for the building blocks of life. In the quest to understand our place in the universe, we are inching ever closer to some of the biggest breakthroughs in all of science. Within the last several years, astronomers have found a number of planets that could harbor life. But the secrets of how life begins are likely shrouded within the cold gas and dust of interstellar space, a realm we've only begun to explore.
Well, the common thought was that there's no way molecules would ever be able to form in the very harsh conditions of interstellar space. You have large amounts of ultraviolet flux, X-ray flux, cosmic rays, newly forming stars creating shock waves that travel throughout the interstellar medium. All these things are going on in these environments, and still large organic molecules, the molecules that make up life, are forming, and they're forming in large abundances in these environments. The solar system and these planetary systems had to form out of this circumstellar material that contains all these different organic molecules. So we're all made of the interstellar medium that is floating between the stars.
At the University of Virginia's Center for Chemistry of the Universe, a team of enterprising scientists is figuring out how complex molecules form in space, a science called astrochemistry. Using a specially designed reaction chamber, they recreate the extreme conditions of interstellar space.
But what you shouldn't really feel bad about are the molecules that we're putting into the chamber back there. We're not torturing them, but what we're trying to do is get them to react.
From stocks of known chemicals, they are creating new molecules.
Every line here is a
new molecule. Many of these molecules that are formed have never been seen before, ever.
Astrochemists are building a database of ever more complex molecules that astronomers can use to identify new chemicals they find in space.
Just for cursors to
These experiments will guide ALMA scientists in their quest to answer the age-old question, are we alone?
What we're going to be able to do now with ALMA is to make chemical maps. And this could have a lot of different implications, especially for astrobiology, where we actually want to see where do the organic molecules, the molecules that make up life, where do they actually form in these regions of newly forming stars. Astrobiology might actually evolve into astrozoology or astrobotany, where we're actually studying plants and animals on other planetary systems. And it's very exciting to say that we're actually starting that first step, starting now.
High in the Atacama, ALMA is preparing to open a new window on the cosmos. 9 antennas now stand ready to make the highest resolution millimeter observations in history. Tonight, the team will focus the array on the star TW Hydra
how's it going?
to find hard evidence of planet formation.
TW Hydra is a very young solar system in formation. We see signatures in TW Hydra that suggest the existence of planets. What we need ALMA for is to really hammer down and say, you know, this is really a planet orbiting this star that's cleared out this gap in the disk. And TW Hydra is so much better for this because it's 3 times closer than anything else we have.
So we've got a little while to wait before we can look at the phase calibrator, but it looks like the atmosphere is quite
The
safe.
operator turns all 9 antennas on the young star and opens their apertures. As the light from space floods in, the antennas stay locked in precise synchronization. And the correlator churns out a steady stream of entirely new data from space. The observation is a success.
Oh, look at that. The CO is just booming in. This is fantastic. Absolutely.
At 2 hours, it is the telescope's longest to date. With so much data, it takes the team the rest of the night to make actual pictures. ALMA's images are computerized interpretations of the telescope's data. Different colors represent varying intensities of light.
Awesome. So you actually see the depression in the middle of the velocity field.
Oh, that's cool.
Even these early images show previously hidden details.
One of the things that's obvious to us just looking at this straight off the bat, you would expect it to be a little bit brighter in the middle. So there's a hint of some depression in the middle.
By the way, the other reason it jumps down.
This depression is further evidence that a newborn planet is just forming in the disk, clearing out a path of matter as it grows in size.
As ALMA continues to add antennas and add capabilities, we'll be able to get not only more sensitive imaging, we'll be able to get to higher resolution, which will mean that we'll see finer detail. It's just opening the door. We're just going to blow everything out of the water that's been done. I mean, it's going to be so much more fabulous in terms of what we can get out of it, that it's really sort of a new horizon.
As work continues and ALMA steadily grows in size and complexity, the landscape of astronomy is beginning to change forever. With each new antenna, we get a clearer picture of the story of the universe and our place within it. Even in well-known regions of space, astronomers are uncovering new worlds of knowledge, showing us where we come from, and undoubtedly, confronting a host of entirely new questions.
Astronomy is unique in a science in that we can use it to understand where we came from.
Nature is cleverer than we are. Just when you think you know everything, you have a surprise.
Every single field you can think of, from our solar system to star formation of all masses in our galaxy and nearby galaxies, to detecting even light from the first stars that formed. I don't think there's any field of astronomy that will remain untouched by the advent of ALMA.
The big question is, how many solar systems turn out like our own, where we have habitable planets like Earth? How often does that happen? And what are the processes that make that happen? ALMA's really going to break this field open.
The name ALMA in Spanish means soul. What ALMA is doing is looking at the soul of the stars.
Autoridades internacionales, nacionales, regionales y locales. It is an honor for me to welcome you to the ceremony in which we will inaugurate the Atacama Large Millimeter submillimeter array known as ALMA.
After 30 years of planning and more than a decade of construction, the ALMA telescope is inaugurated in the presence of world leaders, foreign dignitaries, and scientists who have dedicated much of their lives to this accomplishment.
Thank you very much.
Greetings from the International Space Station. As we look down upon the magnificent Atacama Desert high in the Chilean Andes, we can see the results of an immense effort by the nations of the world to study the universe in new ways.
We congratulate the scientific communities of North America and Europe and East Asia on today's achievement. All the very best to you, and enjoy your new discoveries.
At the array operations site, the full complement of antennas has endured some of the harshest conditions on Earth, while undergoing routine maintenance and frequent upgrades. The first full-scale observations are already changing our understanding of the cosmos and taking us deep into new areas of space. "450 light-years from us, in the constellation Taurus, two newly born stars revolve about each other in a binary system. Their brightness obscures planet-forming disks encircling the stars. But when observed in millimeter and submillimeter light using ALMA, the disks shine as bright or even brighter than the stars. In the clearest ever image of the system, astronomers discovered that the planet-forming disks are surprisingly misaligned with their star's orbital plane and likely stay off-kilter for the rest of their lives. Closer to us, at around 175 million light-years, the star TW Hydrae is revealing even more about the birth of our solar system, this time in the form of something never seen before in a planetary disk: snow. By imaging molecules normally destroyed in the presence of carbon monoxide gas, astronomers using ALMA were able to infer a snowline of frozen carbon monoxide particles encircling the star at a distance of 2.6 billion miles. The first ever image of this phenomenon supports theories that snowlines contribute to planetary formation, much as they may have done nearly 5 billion years ago in our own solar system. These remarkable discoveries and many others have been made with ALMA's antennas close together. Recently, the telescope was reconfigured for the first time to allow long baseline observations, and the increased resolution resulted in a remarkable and unexpected discovery. Returning to the constellation Taurus, in the distant dust clouds surrounding the star HL Tauri, astronomers captured stunning evidence of how planets may form in an extremely high-resolution image.
The first time I saw this image, I thought it was actually probably a simulation. It was just way too good. This star, HL Tauri, is about 1 million years old. And as we look at the star with the ALMA telescope, we see gaps in the radio emission in this disk that's orbiting the star. And quite likely those gaps are being caused by planetesimals, young planets which are forming around this star. This is really, I think, the first example of the type of science that ALMA will be doing for many, many years now. It could be that as we look at more objects like HL Tauri, we're going to see more complex disks. We will actually, at the higher frequencies, may be able to see the actual planets causing the gaps in the rings. So it's an incredibly exciting time, and it's the start of a long journey for ALMA.
Are you getting a TV picture now, Houston? Neil, yes, we are getting a TV picture. You're in our field of view now. That's one small step for man, one giant leap